Okay, you're still recording. Yep. Just let her rip. Okay. I can do it.
Nephew, can be quiet.
Well, good morning. Can everybody hear me? Yeah, this is an interesting handheld mic I have in my hand here. It's not exactly supposed to be a handheld, but it works. Whatever works, right? So, have you had a good morning?
Yeah.
Yeah, well, welcome to Cookeville, Tennessee Tech, the Department of Chemistry. It's a pleasure to welcome you here today. We have a little show for you, some chemistry demonstration, and the Institute of Liquid Nitrogen Ice Cream Experimental Studies. Did I say that right? It's a long name. They're gonna make some liquid nitrogen ice cream for you too. If you've not seen that before, they can just make ice cream in just minutes. It's incredible and it's delicious. My name is Jeff Bowles. I'm the chair of the chemistry department. My role is simple today. It's to say hello and introduce a few people to you. There are several faculty as well as students and student members of the American Chemical Society, as well as even, I think, some new students that are going to assist in putting on these demonstrations. So I hope you all really enjoy it. Dr. Dan Swartling to my right coordinated this event. He's an organic chemist in the department. We have other faculty here, Janet Kuntz, Chad Resniak. Who else is here? Derek. Yep, Derek Cashman up here filming me right now. So I guess I better be careful. It looks like a lot of people are filming me right now. Actually, there's a lot of things that are film worthy today. So I'm going to be like you, and I'm going to sit down and I'm going to enjoy the show.
Before we get started, Janet Kuntz wants to come up and talk about the 5K race coming up, just briefly. So you want to say some words?
So we have a 5K fundraiser to help the student clubs here in the department. We have the American Chemical Society, the ACS Club, the ASBMB, American Society of Biochemistry and Molecular Biology. It's ASBMB's event that they started, and they give the proceeds to help all the clubs here in the department. And they help travel to national meetings, provide outreach activities for the community. There's all kinds of really amazing things that our clubs do with the proceeds from the race. And the race is November the 2nd on Saturday at 10 a.m. Dr. Dan Swartling makes a big boom. It's really exciting for the start. We're having chip timing this year, athletic shirts. Dr. Swartling, Dr. Bowles, a lot of our faculty come out, and Susanna Schisler coming up. She's going to be, come on, let's all give her a round of applause for all the work she does. She has done an amazing job getting sponsors, so we'll have sponsors on the back of the shirt, getting all the volunteers. This will be all the volunteers telling you where to go will be from our chemistry department student organizations. So we really want you to help us spread the word. The price goes up October 2nd, so that's coming up this week. It's going to go from $30 to $35, and then we're going to order our t-shirts October 15th. The race is November 2nd. All the information is at goldenhelix5k.com.
Okay, we want to welcome you guys, especially if parents have students that are going to be participating today. I thought we'd start out with the periodic table song. It's one of my favorite songs. This is chemistry. Chemistry is a study of matter and its transformations. We have the biggest cheat sheet in the room you can see on the walls, and it's arranged for a reason, the way it's arranged on the wall. We'll start off with a song, and if you know the words, you can sing along. We'll actually shut the lights off here momentarily.
Aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium. And iodine and thorium and thulium and thallium.
I actually know this song.
There's yttrium and terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium.
You give that to dead chemists. Barium.
There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercurium, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, kryptonium, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
So those are the Lego set, the building blocks of chemistry. We use those routinely to make all kinds of new stuff, things that we can use in everyday life. Let's start out with a trick today, and we'll call up especially someone who's got parents here today. Oh, let's start with Joey Cooper. Just to pick on him. Where's he? Oh, you're okay. You can put the camera down momentarily. We'll what we're going to do is we're going to take hydrogen peroxide. First of all, state your name and your major and where you're from, and your year in school.
That's awesome. Hi, I'm Joey Cooper. I'm a freshman and I'm a chemistry major. Oh yeah, I'm from Murfreesboro, so that's it.
Murfreesboro.
Okay, so what we're going to do is basically put hydrogen peroxide in this container. This is 30% hydrogen peroxide. So go ahead and open the container, fill it about an inch full, 2.5 centimeters full. .5 centimeters, not millimeters. It's about up to here. Okay. He's a freshman, he doesn't know yet. Keep going. I'll tell you when to stop, how's that?
Yeah, that works.
A little bit faster.
More's better.
Yeah, more's better. I'll learn that the hard way. No, not on you maybe, but
Okay.
Okay. All right, that's probably enough. Okay. So you can probably see some bubbles in here. There's actually oxygen and gas coming off. This actually decomposes over time. Peroxide goes to water and oxygen. It's a very slow reaction. It takes years for this reaction to actually go to completion. And as chemists, oftentimes we're employed not to so much come up with something new, but to produce something we know how to make, but in a shorter period of time. So we want to make this reaction go faster. So we're going to add a catalyst. A catalyst is something that speeds up a reaction without being consumed in the process. This is manganese dioxide. We should tap a little bit in and see what happens.
More's better.
No, don't listen to him. Okay, in this case, you might want to put a little bit more. That's good, that's good, that's good, that's good.
Oh, yeah.
Okay, so watch what happens now. We're taking a reaction that takes years. It's going to go in just a brief seconds. So notice it's starting to fizz a little bit. You sure you added enough?
Do I need to add more?
No.
More.
It's going, it's going. Once it generates enough heat, it'll actually start doing what it's supposed to, but it's starting to go now. We started off with fairly cold peroxide. Getting a secret message from one of my spies over here.
Is that the fire department? They're just concerned.
Yeah. Last year I started out with the school year with a visit from the fire department. That was kind of fascinating. Okay, it's building up some heat now. It's actually starting to go. So again, we're taking the peroxide, we're decomposing it into water and oxygen. And we're taking a reaction that usually takes years, and it's going to go in just a matter of seconds. That's actually just steam and water vapor. That's actually water vapor. Pay no attention to the screen. Oh, that does look kind of cool. Okay, so he's taking a reaction again that takes years because it's a very slow process. We've speeded it up just a matter of minutes. How can we prove that the catalyst is still present? We said the catalyst speeds up a reaction while being consumed in the process. So how can we prove the catalyst is still here? Put more in, of course. So pour some more in, and we'll see what happens. Well, I stand back this time. Go ahead. Go ahead. You have goggles on. That's probably enough. Okay, so we proved the catalyst is still present because it can still do its job. Once again, once it hits peroxide, yeah, go ahead, take a picture. Decomposes again into oxygen and water vapor. So you're a freshman. Is that your first reaction?
Actually, we had some sulfuric acid and sodium carbonate in the lab earlier. So.
Okay, I won't ask you how that turned out. Let's give a round of applause for me.
Good job.
Who did I steal these from?
Okay, who to pick out next? Who the mic go? Where is Rebecca Lampley? And do you have safety goggles? Okay, state your name, your major, the year you go to school, and where you're from.
I am actually a triple major. I'm a biology, biochemistry, mechanical engineering major. I'm from Nashville, Tennessee, and I'm a senior, so I'll be graduating in May.
You're a senior?
Yes.
Then you should know chemistry, right? Right. We have two solutions we're going to mix. This is solution 1 and solution 2. What I need you to do is measure out 42 mils of this one. Well, 40. I'm an organic chemist, so if you go for 40, it'll be 42 by the time you get there. We're not known as being very precise people. Although everything we do actually works out. Believe it or not. So about 40 mils. Yeah.
It's about 48.
48? Okay, that's a bit too much.
Okay.
No, for this one. That's good enough. 40 mils. Okay, now add 100 mils of water to that one. Put it in here, then add 100 mils of water to it. This is distilled water. So add 100 mils of distilled water to that one. We did use this one, right?
Yes.
Good. This is a foolproof demonstration as long as you remember one thing.
you don't measure the same solution twice. Because if you add the same thing to itself, nothing happens. And then I have to explain why things happen the way they do, which I'm good at, actually. Like, why did your hair catch on fire this week? I'm just reminded that he still has a videotape of the only time I've caught my hair on fire in class. He's threatening to give it to the faculty for Christmas presents. Okay, so we have solution 1. Those are called stock solutions. We dilute those down. Now, try to get about 40 mils of that one. And that should be more critical than the other one. So aim for 40 if you can.
I'll have to put it in the big one.
Wow. Exactly. Okay, so put that in here. You must have had a quant recently. Okay.
Yes.
Now put 150 mils of water into that container. Notice for people like me, I even put the caps in different colors to remind myself which ones to use. Make sure I don't measure the same one twice. So there's 100. And 50 more. Okay. And now, what do you think we're going to do? Okay, so we're going to mix them together. So mix the small one while I stand back. Mix the, put this one very rapidly into the big one and hold this up for everybody to see, and we'll see what happens. Ooh, that was kind of quick. We actually turned 2 colorless solutions into a colored solution. That's actually iodine that we produced. It's the iodine clock reaction. So we can determine the amount of time it takes by diluting it down. The more diluted it is, the longer the time takes. So let's do that again a second time and use 20 mils. 20 mils of each solution, and we'll put those in containers. So solution 1, 20 mils. That was pretty fast. So that was 20 mils, okay. And 150 mils of water. Still water. Yep, 150. That's probably okay.
More is better.
More is better. 20 mils of bisulfite solution.
It's not for government work. There we go. 150 mils in that one also. So we're cutting down the volume of stock solution used, and we're diluting it even more this time, so it should take longer, in theory. So there's 100. And 50 more. Okay, and now, just like last time, pour the small one into the large one and hold it up for all to admire. Kind of as fast as you can. There we go. Stand better this time. Ooh, took longer this time, didn't it? So, again, we can control the time by controlling the amount of water we have. The more dilute the chemicals are, the longer it takes. This can go from instantaneous all the way to an hour, depending upon how we dilute it down. It's called the clock reaction because the same chemicals at the same concentration will always change that color in the same time period, number of seconds. So let's give her a round of applause for doing that. Okay, Janet wants to do one of her favorite tricks, so we'll call on Mrs. Goodness to come up here.
All right, we have, I'll go ahead and let you tell your name and major.
I'm Luke Parrish. I'm a pre-med biochemist, and I'm from Waynesboro, Tennessee.
And you are a
I'm a freshman.
Today we're going to, go ahead and advance the slide one time over. Talk about universal indicator and how it helps us understand information about solutions. So what I'm going to start with is we have some tap water, and I'm going to use this universal indicator, and what information can you get from this universal indicator with our tap water? What color do you see? Yeah, so we have a green color.
It's not very good for fish.
Say it again?
It's not very good for fish.
Well, it depends on the fish, but green neutral. And we have here a solution. What does this information from our indicator tell us?
Yellow.
It's yellow, so what does it tell us about the pH? It's acidic. If I add base, so here I have a dilute solution of sodium hydroxide, we're going to get to, let's all watch and see what happens when I add base. Did this one for TTU. So here, Lucas, what I want you to do is hold this, and I'm going to add universal indicator. This is tap water. Now that we've seen this, what happens with tap water, what do you predict is going to happen when you take universal indicator and add it with tap water? Universal indicator to tap water. Yeah, so let's see. Now, chemistry is the study of matter. Matter is just the fancy word for stuff. And the changes it undergoes. So that's the big fun part of chemistry, is what are the changes that matter undergoes. So what we're going to do now, let's go ahead and swirl that. You can give it a better swirl than that. There you go. Give it a little bit more. And then now, what I'm going to do is make it so that you can see a little bit better. I'm going to hold this. Can everybody see? And now, Lucas, what I want you to do is exhale through this solution. Get a big, deep breath. And everybody, see? Keep going, get another breath. Anything happening? Watch closely. So scientists make good observations and careful observations. What's happening? He's got no arms. So thank you, Lucas. Don't pass out, please. That's good. So we've changed the pH of the solution. The pH has dropped, meaning that this solution is now more what? More acidic, right. And so does anybody want to guess why this happened? So I hear a lot of people saying carbon dioxide. Let's test that. Here I have solid carbon dioxide, dry ice. So we have dry ice, incredibly cold. So I'm going to put a glove on. And I'm going to add, Lucas, can you hold this so that we can see? Got our tap water. I'm going to add some dry ice to our tap water, and what do we observe? Yeah, that's the water vapor condensing above. And what's happened is the carbon dioxide reacts with the water. It reacts with the water to form carbonic acid. The pH drops. We observe a color change with our universal indicator. So now here what I have are two other solutions. I have a solution A and a solution in B. And what we're going to do is add some dry ice to both of them. Make observations. So can you all see these two? All right. Huh. What's happening? This one, same observation that we saw here, this is just tap water. I add tap water, I put my dry ice, which is our solid carbon dioxide. The carbon dioxide reacts with the water to form carbonic acid, the pH drops. Now what's happening here? Anybody want to explain this? It's still green, so what do we know about the pH of this solution? It's still neutral, so can anybody here explain this? What type of solution do we have? Come on, chemistry. Yell it out. A buffer, right. A buffer is a solution that resists changes in pH when you add an acid or a base to it. So what we have here is a solution of baking soda and water. Baking soda is sodium bicarbonate, and it acts as a buffer to resist the change in pH from the carbon dioxide.
I don't know that.
Fun stuff. Acids and bases, universal indicator. You can come and play with this afterwards if you'd like to. It's really exciting when we add a little bit of acid, add a little bit of base, observe the color changes. So I'll turn over to Dr. Swartling.
Okay, my favorite person to pick on is who? Ariel? No, I got you down for the next one. My favorite person to pick on is Veronica Sublett. You guys all know that. We're going to go through some of this stuff a little faster so we can get some more stuff in before we go to the ice cream. Veronica plays rugby, so she's used to danger.
A lot of it. I got bit by a dog yesterday too, so I mean, it's all good.
State your name and your major and where you're from and who your parents are.
I'm Veronica Sublett. I'm a pure chemistry major. I'm a junior, and I'm from Knoxville. My parents are Jim and Kathy Sublett over there, and then my boyfriend Shane Breeden. And my grandfather was Dr. Robert L. Sublett. He was head of the chemistry department for several years, so a long time ago
Okay, we're going to simulate combustion in car engines now. which is always fun. Oh yes. This is methanol, and this is a bottle with 2 screws in it with a gap called a spark gap. A 4th grader, I think known as a 5th grader, actually gave me this idea. For years I've been trying to hit certain ceiling tiles and avoid the lights in this room. He said, why don't you take a laser pointer so you can actually aim for the tile you want to hit. 5th graders are our future. Some of them are extremely smart. So, I don't know why it took me 18 years to figure this out. But it seems to work fairly well. So, we're going to put some alcohol in here. Okay, give it a good squeeze.
What's he doing?
More.
More is not always better. Yeah, that's good enough for me. Okay, now, put a stopper in it. Put it in fairly tight. Now, the reaction, which we could write on the board, is the methanol combines with oxygen to form carbon dioxide and water. It should be spontaneous. Exothermic gives off energy. What do we see?
No.
Exactly, we see nothing. A future chemist right there. We see nothing because we have to initiate this reaction, just like in your car. We have to initiate this with a spark. You right-handed?
Yeah.
Okay, you might want to put a glove on. Which hand are you going to hold it with? Yeah, that's a good question.
Let's go with the
With the left? Okay. All right. So we're going to simulate what happens in your car by using the Tesla coil.
Do you have an aim for where you want it?
That's your job. We don't want to hit lights because the dean is here. This is not guided by wires or the laser. It's a dumb cord, not a smart cord. That's good enough, okay. So, when you're ready, hit one of the screws. Let's do that again. More is better. We're going to add more alcohol, so add more alcohol. Add more alcohol. That's probably more than enough. Oh, that's way too much. Now, we're scientists. It's got to be the same stopper with the same coil, with everything else being the same. The only difference now is we added more alcohol. So go ahead and shake that up. Shaken, not stirred, like James Bond. And we know that it's the vapors that actually are doing the reaction, not the liquid. Okay, that should be enough. Okay. So once again, go ahead. We'll stand way over here. What did you do this time?
It's your fault.
It's not my fault. Derek's taking pictures over here. Okay, you're a chemist. In fact, you're a senior, right?
No, junior.
Oh, junior? Okay, then you don't know the answer yet. What is wrong? We know we have a spark, because you can see the spark. Okay. It's the same cork. It's the same cork, the same alcohol, everything's the same. What happened this time? Why is it different the second time? No, it's not too much alcohol, but you're getting close. Plenty of alcohol. Not enough oxygen. We used up all the oxygen the first time. We said the alcohol has to react with oxygen to produce CO2 in water. Without oxygen, there's no combustion. That's why we have things like fire extinguishers to exclude air from things to keep things from continuously burning or putting out fires. So we're going to put air back in here. It's like CPR in a bottle. Chest compressions. There we go. Tastes like vodka. That should be enough. Now, the same bottle, the same alcohol, the same cork. Go ahead and shake it.
The hypothesis was, without oxygen, there is no combustion. If you're playing along at home, let's see what happens. So, go ahead and do that. Put the coil back on. I don't know, how's your aim? Oh, that's good, that's good. All right.
Making sure.
Yeah. So, was the hypothesis correct? Without oxygen, there's no combustion. You need oxygen. Oxygen is required for the reaction to take place. So Veronica has passed Jim, Kim, and everything else. Let's give her a big round of applause. Now Ariel can come up. We have a special thing just for Ariel today. Yay. Okay, name and year and major and where you're from.
Hi, I'm Ariel. I'm a freshman. I'm biochemistry and French major going pre-med, and I'm from Knoxville, Tennessee.
Very quickly, your mission today is to measure out 10 mils of each solution. We're going to put a stopper in here. Are you right-handed? Okay, you're going to put your thumb on the cork and shake this as hard as you can until I say stop. Okay? So 10 mils, you can kind of read it. That's the 10 mil markers right there. And this one is not so critically get exactly 10. That's close enough. Just so it's about equal volumes of the three solutions. So there's solution 1, which is B. And we're going to put 10 mils of A. Now there's an actual order to this. We do this on purpose. We actually do. So B, we put C in last, and you'll see why in just a minute. Okay. And now 10 mils of B. That's good. Okay, go ahead and have that one. Now, yep, put your thumb over the cork and shake it as hard as you can until I say stop. While I stand over here. Keep shaking it. Keep shaking it. Keep shaking it. Keep shaking. A little bit harder because you may want to switch hands if you're getting tired. Okay. You could dance to the periodic table song, but I don't want to humiliate you that much. We reserve that for seniors. Should we make her stop? Okay, make her stop. What do you see? Ah, you see yourself, apparently. Okay. What we've done is an oxidation reduction reaction. One of these solutions contains silver. One contained a solution of glucose under base conditions.
We oxidize the glucose and reduce the silver. If the glass is really clean, it plates on the sides as a mirror. It's called the silver mirror reaction. And at Christmas time, we like to make ornaments. We do all kinds of stuff around here that's kind of fun. Let's give her a big round of applause. Okay, who haven't I picked down yet? Caleb Ray, is he here? Uh-oh. All right. Let's pick on somebody else, too, at the same time. Bryce Hall. Bryce Hall here. Okay, state your names and your major and the year in school and where you're from.
I'm Caleb Ray. I'm a freshman from a little town called Humboldt, Tennessee, right outside of Jackson, and I am a chemistry major with a business concentration.
I'm Bryce Hall, and I'm a pharmacy and health science chemistry major, and I'm from here, and I'm a sophomore.
Okay, who wants to be the victim and who wants to be the pastor? In other words, who wants to sit on the stool? Neither one of you. Face the audience.
Lab coat on.
Hey, you might want to have a lab coat on for this one.
Yeah.
Yeah. Somebody knows what can happen when this goes wrong. It's only happened once, just like my hair on fire. This is water, distilled water. We're going to pour some into a glass. And just to prove to you it's water, I'm going to pour it back and forth a few times.
How does that prove it's water?
It doesn't, does it? But it proves it's a liquid which flows and adopts the shape of its container. And it was in a jug marked distilled water, which by Tennessee OSHA and EPA regulations has to be properly labeled now. So, good questions. We're going to pour that into a glass. We're going to play a variation of the shell game. Face the audience. And you're going to tell me which cup is it in. 1, 2, or 3.
Where's the water?
One, 2, or 3. Which cup has the water? 2? Okay, you're supposed to pay attention. Okay, because I wasn't that fast. You could actually follow it. All right, cup 1. Pour it over her head. Ooh, empty. Okay. Cup number 3. Also empty. So where's the water? Cup number 2. Where did the water go?
It disappeared.
Excellent observation, and it's not too far off. The water's still in here, but it did disappear. We did something chemically to it. We made the water be absorbed by a powder that absorbs up to 400 times its weight in water. Same water they put in super absorbent diapers. One of the 10 modern miracles of science. So what goes in doesn't come back on your lap. Okay? Also used in potting soil, they call it water locks. So when we have hanging baskets, they don't dry out as much. But this powder absorbed the water, so the water's still here, but magically it stays in the cup because it's bound to the powder. So let's give our victim a big round of applause. Okay, now it's time for ice cream. We're going to get set up to make ice cream, and then we'll call you down when it's ready. We're going to make 5 gallons of vanilla ice cream. We're going to make a gallon of chocolate mocha, and we're going to make a gallon of peppermint Oreo on that station. So if you've had practice, we need some help down here making ice cream. For those of you that didn't get a chance to do a trick, you can also at this time introduce yourself to the audience and state your major and where you're from.
Oh, hi. I'm Alexandra. I'm from Venezuela, and I'm a chemistry major. Hello, I'm Rosa. I'm from Peru, and I'm a biochemistry major.
Hey, I'm Tim. I'm a biochemistry major, sophomore from Nashville, Tennessee.
I'm Adam. I'm a freshman. I'm from Oak Ridge, Tennessee, and I'm a biochemistry major.
I'm Amanda Werland from Tullahoma, Tennessee, and I'm a chemistry major.
I'm William Morris from Lawrenceburg, Tennessee, and I'm a senior.
I'm Nathan Rigsby. I'm a junior biology major, and I'm from Cookeville, Tennessee.
I'm Patrick Stone. I'm a junior health science biology major from Lynchburg, Tennessee.
I'm Rebecca. I'm from the North City, and I'm a biochemistry major, and I'm a junior.
How's everybody doing? Everybody's just saying their name. My name is Joshua Crago. I'm from Tullahoma, Tennessee, and I'm a microbiology major.
I'm Skylar.